First of all, I would like to thank for this invitation. It is a great pleasure and a great honor to be in Tokyo virtually. And the topic I am going to talk about is strongly motivated by applications, but it has several roots into convex geometry and geometry of tessellations, and you will see these connections. So my co-authors on this work are Doug Jerolmak, who is at University of Pennsylvania, Ferenc Kuhn, University of Debrecen, János Török, Péter Bálint, and Krisztina Regős, who are at my university. This is Budapest University of Technology and Economics. So first, let's talk about the inspiration. On the left side, you see the bust of Plato. And as you know, Plato had this theory. The regular solids have been named after Plato. They are called the Platonic solids, but they were not discovered by Plato. Actually, they are described in the 13th book of Euclid. And actually, Euclid proves that there are only 5 regular solids in 3D space. However, Plato recognized their philosophical significance, and he associated these regular solids with the elements. And these elements are the earth, the fire, the water, the air, and the universe. Now, in the 21st century, we might be tempted to think that this is just an old metaphor, and it has nothing to do with actually nature. So this is just about some outlandish philosophical thinking. I am not arguing about philosophy, but let me just say that there were 2 people who were very much in favor of Plato's theory and who argued that the theory has actually roots which are connected to natural phenomena. And these 2 people are Frank Wilczek and Werner Heisenberg. I hardly need to introduce these excellent physicists, both having the Nobel Prize. And in particular, Heisenberg made a lot of talks about Plato's theory, but also Wilczek. And the argument was that at the core of the theory is that matter consists of very small, identical, small, and symmetrical objects. This is the essence. According to Wilczek and Heisenberg, this is the essence of the theory. And this is, according to their view, the first description of the atomic world. Now, this is still a symbolism, but it has many connections now to what we believe is the world, actually, the physical world, or the physical world at the microscopic scale. Whether this theory has anything more to do with nature, that has not been discussed until now. And I will show you an argument which still doesn't prove that it is directly connected to nature, but it will give you a second thought, I hope. So if you go out for a hike, at least here in Budapest, but I think it is the same in Japan. So if you go out and you see crushed, fragmented rock, what you can see in this image is crushed dolomite. Now, if you pick up a few of these rocks, here I picked up a few of these rocks, you can observe that these rocks have sharp edges and sharp corners, and they have relatively flat faces. So in our mind, they are very close to polyhedra. And here I show a few of them enlarged. And as you can see, there are very good approximations of this rock using just convex polyhedra. And now we count the numbers of faces, edges, and vertices on this polyhedra. These are just 7 on this image. And for the average number of faces, we get 6.4. And for the average number of vertices, we get 8.6. This is a very small sample, but still these numbers are already a little bit suggestive. And if I would give this talk physically, I would certainly ask the audience, but in this setting, it is hardly possible. What is your guess? And I don't know. I am asking Toshitaka. Is it okay? Is there any way to ask the audience, or is that not really working in this setting? I don't want to press it. I was just wondering.
So if you have some questions to audience,
yeah,
the audience can write up chat or Q&A the question.
Okay.
Answers.
So that it's maybe a little too complicated. I will, if I have questions to you, I can ask questions from you.
Yeah.
So it is 6.4 and 8.6, and I would like to ask, what does it remind you of, these two numbers?
No, I don't have any idea.
Okay, no problem. Then no problem. So now we did a little bit more of experiments. These are just 7 pieces. And we went to another place in Budapest and we collected 556 pieces. And we made the same numbers. We counted the same numbers. And now the averages were 6.03 and 8.01. So does this suggest anything to you?
This is close to cube, yes.
Yeah, so we could finish the talk here. So basically, we found that the averages are so close to the cube that this cannot be a coincidence. And this is a very interesting observation. And you can do this in Japan. I encourage you to do it in Japan, actually. Now, we also observe that if you look at the rock outcrop, you can see long straight lines. So that is also rather characteristic of these cracked surfaces. So there are like these long cracks going through the area. And this is another one. This is not in Budapest. This is in Helsinki. And this is not dolomite. This is granite. And this also has these long straight lines. And this is also very characteristic of fragmented rock surfaces. Now, as a model for this process, we use convex mosaics. Convex mosaics are tessellations, and I will first talk mostly about two-dimensional tessellations, but I will also talk about higher dimensions. And we tessellate the space with non-overlapping domains, which are disjoint. And we require that they are bounded both from below and from above. So we cannot have arbitrarily large and arbitrarily small domains. And if we require that every domain is convex, then it is very easy to see that they have to be polytopes. So in 2 dimensions, they have to be polygons, and in 3 dimensions, they have to be convex polyhedra. And we have basic variables. Now so each polygon will be called a cell of this tessellation, and the number of cells is denoted by capital V. Oh, sorry, number of cells is denoted by capital F. And where these cells meet, the points where they meet, they are called nodes, and the number of nodes is denoted by capital V. And we can also count the corners. So where 2 edges meet, and the number of the corners we denote by capital N. We also assign degrees So a cell has a degree, which is just the number. This is a polygon or a polytope. This is just the number of vertices of that polygon. That is the degree. And the degree of the node is the number of polygons meeting at that node. We can have two types of nodes. In one case, every angle is different from pi. And in the other case, there is an angle which is pi. So this means that the vertices of polygons are on the edge of another polygon. In case of regular nodes, it is also called a face-to-face mosaic, where edges meet edges, faces meet faces. And the other type, where vertices may lie on edges of other polygons or polytopes, is called irregular or non-face-to-face. Now, we can compute the averages for a given domain of these degrees, and for the nodal degrees, capital N over capital V, and for the cell degrees, capital N over capital F. Now, of course, we require that as we increase this domain and go to infinity, that these averages converge. This is a requirement. It's called a balanced normal mosaic. We don't deal with other types of mosaics. And the plane spanned by these averages will be called a symbolic plane. Now, I will talk about a very particular type of convex mosaic, which is called a primitive mosaic, or it is also called a hyperplane mosaic. So here is the granite wall, and the model which we imagine is just a tessellation by using straight lines, bisecting always the whole domain. And you can do this in any dimension. You use hyperplanes, and this is called a hyperplane mosaic. This is a very, very interesting and very nice type of mosaic. It's a convex mosaic, obviously, and this has been investigated to great detail. There are many papers on this type of mosaic. Now, one interesting feature of this mosaic is that you can count, as I said, the number of cells, and you can count the number of nodes. And it is an almost trivial lemma that these numbers are equal. So no matter what is the dimension of the mosaic, and no matter what is the particular random distribution from which you take the hyperplanes, it does not matter. The only thing which matters is that this is generic. So in 2 dimensions, there are always 2 lines intersecting each other. You cannot have degeneracies, but the actual distribution doesn't matter. And in every case, you have the number of nodes is equal to the number of cells. And without giving a long proof, I just give the idea of the proof. If you let the normal of the cell go around the cell, because it is convex, you are going around the unit circle with the normal. And if you go to the node and you let the outer normal of the cells meeting at that node go around, you are also covering the unit circle once. And this gives you a one-to-one relationship between nodes and cells. And this gives you very immediate answer to the averages. Because in 2 dimensions, the average will be 4, because every single node has degree 4. We see it's always an X node. And because we have the same number of cells as nodes, the average degree of a cell will be 4, but it will be not uniform. There will be different types of cells, but on average, they have to be 4. And the nice thing that this holds in any dimension, and in 3 dimensions, we have the averages of the cube. And in any dimension, we have the averages of the cube, the n-dimensional cube. So on average, we have 8 vertices, 6 faces, and 12 edges. So this gives you a very nice kind of general understanding what might be at work in this particular case. So this simple mathematical model does predict what I would call cubic averages. So averages which correspond to the cube. Of course, the geophysical setting, the geophysical process is slightly more complicated. Although the straight lines serve as a good first model for this kind of rocks, there are also secondary cracks, which are not going through the whole domain. They are just local. They happen after the primary cracks in time. Now, in 2 dimensions, it is again a one-line statement that this secondary cracking process. So you do the primary, you produce a hyperplane mosaic with this tiling, and then you take randomly individual cells and bisect them with the red lines. This will not change the average. This is a very simple fact in 2 dimensions. In 3 dimensions, this is less obvious. In 3 dimensions, it will depend on the random distribution how you pick these lines, how to pick these secondary cracking planes. However, we did many simulations, and we found that the average was still 4. The averages were still corresponding to the cube, I am sorry. So we still had 8 vertices, 6 faces. This is not a theorem, but there are some curious statements which have been already proven. I just tell you one statement, which is a convex geometric statement. It is very interesting. So you take a cube, or it could be any rectangular block, so like it doesn't have to be equal sides, and you slice it with parallel planes. In each slice, you get a convex polygon. And each polygon has a certain degree. And no matter what direction you use, the average, if you average over all these parallel slices, will be always 4. So the average slice will have 4 edges. So there are mathematical facts, and there are computer simulations which tell you that even in secondary cracking, the cubic averages, so 6 faces, 8 vertices, are preserved. Now, we did a computer simulation. You can see it on the left-hand side. And we did primary bisection of a domain, which is a cubic domain here, and also secondary, which we call the cut model, the hyperplane mosaic, and the break model. So we took out the fragments and we bisected them also in a secondary phase. Now we compared with the data. So this is the distribution for phase degrees and the nodal and the number of faces and number of vertices for the 556 fragments which we found. And this is the distribution which we found in the computer simulation. And if you overlay the 2 distributions, you see they are stunningly similar. So this means that this model is a very good model of actual rock fragmentation, not every rock fragmentation, but this kind of hyperplane kind of fragmentation. And this explains why we see the cubic average dominantly in nature. So this is the short explanation. If we were in a physical room, I think someone would have raised her hand or his hand already, because the left diagram has 1 peak, and on the diagram on the right-hand side is just zigzag. Now, what is the reason for this difference? This is very interesting reason. On the right-hand side, we see the number of vertices. Now, if you produce polyhedra by cutting them, so you take a big chunk, you cut it into 2, and you always produce new polyhedra by bisections, then in the end, you will end up with polyhedra which are called simple polyhedra. Simple polyhedra have vertices with degree 3. Every vertex has degree 3. There are 3 edges meeting at every vertex. So this bisection always ends up with simple polyhedra. Now, simple polyhedra have a property that the number of vertices is always an even number. And you can see that the peaks are at even numbers and the valleys are at odd numbers. So this, again, you can see a very simple, maybe simple, very nice geometric fact from convex geometry being reflected in nature to a surprising degree. Now, this was just an example. I just told you about hyperplane mosaics, how they explain the cubic averages. Now we want to get a little broader background, what kind of mosaics we have at all, and how common are these kind of mosaics in nature, because I just explained you one type. So again, we are in the same slide, which I showed you before. These are the same variables, the same notation. What I added here, we have the symbolic plane, which is bar n, bar v. This is a symbolic plane. I will talk about the symbolic plane. And we can also have the inverse symbolic plane where we plot the reciprocals of these numbers. This will be also significant. I mentioned that we can have regular nodes where vertices overlap with vertices. And we can have irregular nodes when a vertex is on an edge of another cell. And if we divide the number of regular nodes by the number of all nodes, we get the regularity of the mosaic, which is, of course, between 0 and 1. Now, the general question is, can we express the cell degree, which is V, as a function of the nodal degree and the regularity? This is a general question. And the answers are relatively simple. So let me first say for regular mosaics, where we have face-to-face, in the plane, the answer is very simple. We are on a hyperbola. Every single mosaic is sitting on this hyperbola. I just gave you a few examples. And I mentioned this is a brilliant book by Rolf Schneider and Wolfgang Weil. And all these formulae are in that book. I mean, for regular mosaics for any dimension. Now, one endpoint is this honeycomb, which is 3 and 6, and the other endpoint is a triangulation. We can also have random mosaics on the same plane. I mentioned hyperplane mosaics, primitive mosaics, which are 4, 4. I proved that they have degree 4, both for the nodal degree and for the cell degree. We can have Voronoi mosaics, which are the Voronoi tessellations of a plane. You have a point set and you define the Voronoi cells around those points. These are the randomized version of a honeycomb. And we can have their duals, which are the Delaunay triangulations. Every single mosaic in the plane, a regular mosaic, has to be on that piece of that hyperbola. Now, if we go for irregular mosaics, where we admit also nodes sitting on edges, the situation is more complicated. We don't have just one line, we have a planar domain in the symbolic plane. And well, there are some interesting pieces here. For example, these are the totally irregular mosaics on the left-hand side, which corresponds to P equals 0. We like a brick wall, where every single node is irregular because it is a T node. So a vertex is sitting on an edge. And on this domain, we can again have the randomized mosaics, which I showed you before. And I also show you some simulations. So this is a hyperplane mosaic. And what I do here, as I move to the left, I add secondary cracks. So on the right-hand side, I have a regular mosaic, which has only primary cracks. It's a hyperplane mosaic. And I move to the left, I get to the case which has only irregular nodes. So this is the theory in the plane. I show you now some examples from nature. On the upper left-hand side, you can see this is an image from Mars. taken by, this is a satellite image, not taken by the rover. Below it's a basalt columns. You can see mud. On the right column, you can see this is permafrost in Alaska. So it's a very large tessellation, actually. Below that, you can see a very famous rock in Norway. Any of you who has seen Mission Impossible 6, the final scene of that movie with Tom Cruise fighting the evil guy is taking place on this particular rock. And on the bottom, you can see another type of mud. And then we put these things on the symbolic plane. You can see that they are very well spread, but only in the upper part, only in this upper domain of the symbolic plane. And you can also see the granite wall. One example, which I didn't mention before, is a very interesting example, is the tectonic mosaic. So if you take the crust of the Earth, it is cracked, and you can regard it as a mosaic. However, that mosaic is not a planar mosaic. That's a mosaic on the sphere. So the combinatorial properties will be different. Here is the tectonic mosaic, and you can see that it is located slightly below this hyperbola, but this is not some error. This is an exact location because it is a finite mosaic on a sphere. And the hyperbola is for infinite mosaics on the plane. And if you increase the number of plates, if the tectonic plates the number of plates would increase, the location of that point would converge to that hyperbola. And if we have a small number of plates, then it would go down because we are very deep on a sphere, we have a different rule. So here you can see that all spherical mosaics are here, and only the ones in the limit, when we have infinitely many cells on a sphere, then it converges to the Euclidean case. Now, until now, I was talking about statics. So we see an image and we put it on the symbolic plane, and geologists love to do this because they can compare mosaics based on the location on the symbolic plane. But we can also ask, as these things evolve, so new cracks happen, these things move on the symbolic plane somehow. So there is a dynamic theory. So these mosaics evolve in nature, and you might ask, what is the evolution happening in this mathematical model? To analyze the evolution, we need a few additional ideas and a few additional tools. So this is the same slide as I showed you before. Only the question is now different. So we are seeking a trajectory on the symbolic plane as a function of time. But to have time, we have to define what is time here. And what I am doing, I am defining local events. Now, these events will be familiar because the first event is basically what we have been talking about. So you take a certain number of cells and you bisect them with a straight line. You can have only one cell bisected, you can have two cells bisected, you can have any number of cells bisected. The number of cells, then this will be the parameter m, and we bisect m plus 1 cells. So if m is 0, we bisect one cell. If m is 1, we bisect two cells. In this example, we bisected two cells. In this step, we created 4m plus 4 new angles, m plus 2 new nodes, and m plus 1 new faces. And then other step, which I show on the left-hand side, is a slightly different step. where we turn an irregular node into a regular node. So a T node is turned into a Y node. In this case, we just created one additional angle, no new node, and no new face. It is just a small rearrangement. Now, how do this happen in time? These are discrete events. Now, we have to be very careful now. We put clocks, we assign clocks to the cells and to the irregular nodes. These are ticking clocks. These are Poisson processes. Each clock is ticking like a Poisson process. And each Poisson process has an intensity. They are discrete events. Each clock is ticking. And when the clock gives a signal, at that phase, the event will take place. Or at that node, will turn into a Y node. These are at discrete times, randomly, at a Poisson process. However, we have an infinitely large mosaic. So because we have infinitely many clocks, this will define a continuous time process. Of course, you have to be very careful how you take the limit of in the space, how you expand your, how you define your limit. But you can understand that it's many, many, many little clocks ticking all over the mosaic will ultimately define a process which is continuous in time. So I just summarized all this data in a table, which we call the fundamental table of the cracking process. So I define local events. I assign exponential clocks. To each clock, I assign an intensity, and that gives me a differential equation. Now, how exactly this differential equation is derived is not part of the current talk. But it is an algorithmic thing. So once we define the table, the differential equation is given. And if I change the local steps, you can plug in any kind of local step. I can mention, so for example, we could regard a crack which goes from a corner to a corner. That would give an entirely different evolution. And that gives you a differential equation. As you can see, this equation is written for x and y. X and y are the reciprocals of the nodal and cell degrees. And it is much, much easier to write the equation for these inverted variables. You can compute a lot of things. Once you have an ODE system, you can compute a lot of things. You can compute the attractors, and you have a global dynamics now on the symbolic plane produced by this equation. So you define these local events, which are geologically very meaningful, very easily understood, and actually being observed in nature. So there are geological papers describing these local events. You define them exactly in geometrical terms. You define how they modify your mosaic, and you end up in a dynamical system. And this dynamical system can be now compared to the actual evolution of mosaics. I am not going into that now. I just mentioned that now, okay, we have lots of data, and we can try to match this data with this dynamics. Maybe there will be different dynamics acting on different type of data. So that is a different story. I just wanted to indicate that this theory of mosaics leads to a deeper understanding of the evolution of mosaics itself. Let me say a few words about 3D. Because actual physical fragments are in 3D. And I started the talk with the cubic averages, and they were actually in 3D. Here is a rock fragment. We are talking about actually 3D. Now, we know surprisingly little about 3D. As I explained to you, in 2D, the theory of convex mosaics is essentially understood. In 3D, we know very little. But we can still use the same concepts, and I will use the concepts to explain you how little we know. So we again have the symbolic plane, and on the left-hand side, you see this yellow line. This is corresponding to 2D mosaics. So we can put the 3D mosaics on the same plane as we did with the 2D mosaics. We have these red dots, and the red dots are the 28 uniform honeycombs. This is a rather recent result that there are only 28 of those. They are vertex transitive, so they have only one type of node. And the faces of the cells are regular polygons. And it is a rather recent result. It was best explained by Branko Grünbaum, but the original result is due to Johnson, but he never published it. So it is an unpublished result, but it is a significant result. There are 28 of these. Now, if you look at these points, you see that they are arranged along a hyperbola, but not exactly. And as of now, there is no result, no mathematical result prohibiting a mosaic being at any location on this plane. Although we think there is probably no mosaic outside the range, and we formulated, here are some geometric mosaics, which I mentioned before. So here is a Voronoi mosaic. Here is what I call a columnar mosaic. So you take a Voronoi mosaic in the plane and make it a prismatic thing in 3D. Here is a hyperplane mosaic, and here is the dual of the Voronoi, which is a three-dimensional Delaunay mosaic. Now, we formulated a conjecture with Zsolt Lange that every mosaic, every regular mosaic in 3D has to be in this band. This band is defined by two hyperbolas, and so far, and we proved that you can have mosaics on both of them. So the band is, you cannot make it narrower. We proved it. We could not prove that you cannot go outside, but it looks very much so. But there is no such result yet. So this conjecture, and this conjecture is for any dimension. So if you go to higher dimension, in any dimensions, you get two hyperbolas, which are further and further apart. And in 2 dimensions, the two hyperbolas coincide. And then you get the yellow line. So here are some natural examples. For primitive mosaics, we have this kind of rocks, which are fragmenting in these cubic patterns. For the columnar mosaics, we have basalt columns, very nice. And for the 3-dimensional Voronoi mosaic, which is a rather complicated thing, as you can see, they have the degree, the nodal degree is 4, but the cell degree of a 3-dimensional Voronoi mosaic is 27 something. So it is a very complicated thing. And in nature, it is very hard to find anything like that, because for this you need isotropy in 3 dimensions. And in nature, you always very often have a one direction which is particular because of gravity. And the only example which we found, but which seem to be relevant, are something called septarian nodules, which one picture is over there. They are on the seabed. And here, if the pressure conditions are just right, so it gets into a hydrostatic state, then the crack pattern will be a 3-dimensional Voronoi mosaic. I have one on my shelf, and if you take it apart, you can see very interesting patterns inside. But this is very rare. In nature, what is very common are these primitive mosaics and the basalt columns. And the experiments which we looked at are very close to the primitive mosaics. So that suggests that these are rather dominant things in nature. Now, I gave you some flashes from nature and from this theory of mosaics. And I also explained how it is related to the evolution of mosaics. Now I would like to give one comment how it is related to the evolution of shapes. So shapes are born like this thing, like a fragment. So this is how a natural shape is born in an explosion normally, or fragmentation. And then after a time, it becomes like this. It becomes abraded. It becomes smooth. It could be even something like this. And in Japan, there are fantastic beaches where you can find the most beautiful pebbles. And now we talked about fragmentation. If you are watching this process in time, so from fragmentation until we reach this kind of rounded objects, this is abrasion. And if you want to understand this, you need something which is monotonic in time. It's very hard to find any kind of shape descriptor which is monotonic in time. Say if you look at the axis ratios or the isoperimetric ratio of such an object, that is not always monotonic. One quantity which appears to be monotonic is the number of static balance points, which is rather strange. So if you take a cube and you want to balance it on a horizontal plane, it has 6 stable positions. If you have been playing games, you know that, 6 stable positions. It has 8 unstable positions, the 8 vertices, and it has 12 saddle-like equilibria on the edges. So altogether, it has 26. And if you look at fragmented rock and you count these numbers, the average is around 20. So this is where nature starts this process. And then as they evolve, they end up with shapes like this, which are like ellipsoidal shapes. And ellipsoids have 2 stable points where I have my fingers, 2 unstable points, and 2 saddle points. So they have 6. So the natural shapes move in the range between 20 and 6. And of course, we know that the gumboots has only 2. So if you look at this image, you can see that the cube and the gumboots are not part of the actual natural process. They are outside. They serve something like a bracket. But as a bracket, they have to understand this is a very complicated process, but it is universal. The same thing is going on Mars. The same thing has been going on for billions of years. And it is very hard to describe the complicated process in simple terms. This picture gives you some idea that this is one view of this abrasion process, which is universal and which puts it into a finite range. So every single, if you take up a bunch of fragmented rock on Mars, it will have the same averages. Or if you do it on any other planet. So this is a kind of a universal picture, and these ideal shapes, like the cube and the gumboots, maybe they are just geometric objects, but they help us to understand nature. And as you know, I just wanted to close it by mentioning that one particular gumboot is, there are many in famous collections. Among the most famous is the number 1877. Some of them have engraved numbers, and that is in the collection of the University of Tokyo, and I am very proud of this fact. So thank you for the attention, and I do hope that we will have a